Alright, we're chugging along with Module 2, talking about georeferencing. Last time I talked about ellipsoids, the smooth elliptical surface, geoids, the bumpy gravity surface, and datums, which are made up of an ellipsoid, a geoid, and a coordinate system. I didn't really talk a lot about coordinate systems, so I want to spend a little bit of time on them right now. So to describe a location on a realized, modeled Earth, so a simplified, generalized Earth, we need an ellipsoid for horizontal location, we need a geoid for vertical location, and we need a coordinate system. So now I need to talk about coordinate systems. So what type of coordinate systems might we use? Well, there's a planar coordinate system called the Cartesian system, which comes from René Descartes and some of his mathematics. All of you are familiar with it. An X, Y, sometimes Z coordinate system. And then there's a spherical, sometimes in GIS called the geographic coordinate system, and that uses angles. So a coordinate system uses one or more numbers to locate a point in space. That's what a coordinate system is. So what does a coordinate system consist of? An origin, directions, and unit of measure. So for a Cartesian system, the origin is 0, 0, right in the middle. For a spherical system, it's the center of whatever object, in this case spherical, in our case elliptical or ellipsoidal object. Direction, Cartesian, geographic, we're going to say north, south, east, west. For a spherical geographic coordinate system, we're going to say longitude and latitude. Unit of measure, for the Cartesian system, we're going to use meters or feet or some linear measure. And for the spherical coordinate system, we're going to use an angular measure, radians, degrees. The Cartesian system is going to be really good for flat, planar maps, and the spherical system is going to be good for geocentric maps. Okay, so a geographic coordinate system. That's going to be good for 3D, right? And what does it do? It uses the center of the Earth as its origin. It uses angular units of measure, and it measures from a prime meridian to the east or west, and from the equator to the north or south. So this is kind of a flat depiction of a geographic coordinate system. You can see that there are things here called parallels and meridians. So a line of constant longitude would be what's called a meridian. A line of constant latitude would be what's called a parallel. Now when you look at this, you can imagine constant lines of constant latitude. They're all parallel to each other, and so that's why latitude lines are called parallels. Meridians, though, have to meet at the poles. And so you can imagine that meridians might be parallel at the equator, but they have to somehow bend their way up to get to the north and the south pole. So meridians aren't parallel to each other except right at the equator. So they're not parallels. So you can see here's another depiction that just shows the parallels, the lines of equal latitude. Here's one that shows the meridians, and you can see how the meridians have to curve in to meet at the poles. If you combine the latitude parallel lines and the longitude meridian lines, you're able to specify any position on that top of that surface. Okay, we measure longitude from what's called the prime meridian. And the prime meridian was just defined by default as where all the action was back at the time, and that was the Greenwich Observatory in England. And so the prime meridian is a great circle that cuts through the Earth and includes the center of the Earth, and it runs right through Greenwich. Okay, enough coordinate systems. What's a map projection? Map projection is a transformation from a 3D representation to a 2D representation. Now this says it's of the Earth. It can be of any object that you want to project into a planar map. But for our instances, most of the time we're going to talk about the Earth, so we're thinking about a map projection as going from the 3D elliptical Earth to a 2D map. You can kind of imagine this graphically as an old-style projector. This is an old-style projector. This is the Earth cut in half. The projector shines its light through the Earth and projects it onto a surface. And so in this case it's projecting the Earth onto a flat surface. That will end up being called an azimuthal projection. These projections use the concept of developable surfaces, and I challenge you to say the word developable several times quickly. But there are three basic developable surfaces: the plane, the cone, and the cylinder. So all of the map projections involve some type of manipulation where conceptually you're projecting the surface of the Earth onto one of those developable surfaces. Depending upon which surface you project it on, you're going to get a different looking map. Okay? If you project the Earth onto a flat plane, you're going to get what's called an azimuthal projection. And this is an example of what an azimuthal projection looks like. It looks like a hub of a wheel radiating out to spoke-wise. The spokes would be the equivalent of meridians, and the center of that hub might be the North Pole, depending upon where the plane touches the Earth. If the projection of the Earth is on a cylinder, you get a map that looks like this. And what you'll see in this case with a vertical cylinder and the Earth is these lines of equal longitude remain parallel, the lines of equal latitude remain parallel, but as you look away from the point where the cone or the cylinder is touching the Earth, the rectangles get longer and longer. If you project it on a cone, you get a map that looks like this, and you can tell that that's a conic projection by the way the lines of meridian tend to be pointing in to some type of a focal point up above and outside of the scale of the map. So what do these do? They're not really exactly, except for several of, maybe four of them, they're not really true projections in the sense that you can make one of these with an overhead projector. They're algorithmic projections, so they use equations to do the projections. But what they do in concept is they project the surface onto one of these developable surfaces, and then for the case of the cones and the cylinders, they slice the surface along a cut line and they unroll that surface onto a flat map. So what it produces is a flat map from the original three-dimensional object. Mathematically, these are algorithms that do that. It's not necessarily something you can do on your own with a projector. Okay, the developable surfaces can touch the surface of the planet in different ways. They can touch it just at a point, and that would be called a point of tangency. So I can have a plane that touches the Earth right at the pole. That plane could touch the Earth at any point, but it'll only be at one single point. Where the cylinder is tangent to the surface, it's going to be touching it along a line that goes all the way around the surface of the Earth. So that would be a line of tangency. And where the cone touches would also be a line of tangency, but it wouldn't be an equatorial line. It would be a line that's at some other latitude. Okay, so they can be tangent, or touching it at a point or line, or they can be what's called secant. And you can imagine secant as being the surface cutting through the planet. So in this case, the plane is cutting through, slicing through the planet, and so the places where it is touching are a line, but it cuts all the way through. When a cylinder intersects secant, it's going to be cutting through in two different places. So you'll have two different lines of tangency. And the same likewise for a cone. When it's a secant projection, it's going to have two different lines of tangency depending upon where it cuts through. So up here, tangents, only one point or line of tangency. Down here, secant, more than one line of tangency. These projections depend upon, in concept, where the surface is at with respect to the surface of the planet. So if my map is a long way away from the surface of the planet, and you can imagine the projection occurring from here, I'm going to be projecting this arc onto this straight line. If this line were further away, the straight line would be a larger straight line. So it depends on where the surface is positioned with respect to the surface of the planet. This is in the opposite direction, where the surface is within the surface of the planet. So you can imagine the projection going back in this direction, where this arc of the planet is getting projected onto this flat line. And you can imagine here where if you're trying to fit all of this line into this amount of space, there's going to be some distortion going on. So the distance from A to B in the projected map is not going to be as big as the distance from A to B on the surface of the planet. You're going to have distortion, and that's what I'll talk about in the next video. Okay, not only does it depend upon where your surface is at with respect to the surface of the planet, it depends on where your light source is, or the imagined light source is. So there are 3 different light source types that you can think about when you're making projections. Gnomic is at the center of the planet. Stereographic is at the back, the very back of the planet. And orthographic is like being projected from infinity. So you can imagine that's the one that would look like the way things look like out in space, where the sun is so far back that it's almost like it's at infinity. And again, you can imagine that the projection upon the surface is going to vary depending upon where your light source is. So here's another graphic that shows gnomic. You can see how these short lines are going to be projected into longer lines. This is a different position of the light source. It's going to have a different amount of distortion, and this one is going to look completely different. So all of these things are going to make your projection look different. It's all the same planet, but each projection will look different depending upon where the surface is, where it touches the planet, and where the light source is. So next time I'm going to talk about distortion, and distortion is what happens when you really are scrunching this planet onto a flat surface. And it's impossible to scrunch the planet and have it land on that flat surface so that everything is not distorted. Something's going to be distorted no matter what you do. So next time I'll talk about kind of common types of projections and what type of distortions they have, so that when you make a map you can plan your mapping to minimize the distortion in the area that is most important to you, and to not worry so much about distortion in areas that aren't important to you. So next time we'll talk about distortions.